This is a 3D model of the human intestinal tract, specifically from the duodenum down. Watch what happens as the ambient environment scales from a normal 37 degrees to an extreme 45 degrees Celsius. The biological tissue immediately enters a state of acute thermal stress. To manage extreme energy demands, the intestines trigger automated system-wide recalibrations. This environment triggers a seasonal drift in microbial density. The data overlay shows a massive operational surge in actinobacteria, paired with a sharp depletion across the Bacteroidetes population to accommodate the heat. If clinical trial designers ignore these shifting parameters or rely on static cold weather metrics, their data integrity is permanently compromised. An intervention tested on a winter baseline will yield vastly different efficacy readouts when applied to a summer grid. While this automated shift to a new metabolic baseline is designed to keep the system running, operating continuously at these thermal limits leaves the underlying biological engine highly vulnerable to mechanical failure. Looking at this photograph, it demonstrates the foundational input for systemic cooling. Water functions as the essential coolant in this biological model. It sustains the mucosal layer required to shield the sensitive epithelial wall from particulate friction. This fluid dynamic simulation clearly illustrates what happens when extreme environmental heat outpaces fluid intake. The gut undergoes coolant depletion. The vital mucosal lubrication evaporates completely, leaving the internal surface dry and exposed. Operating the system dry starves specialized maintenance bacteria, like Akkermansia, of their operational fuel. These units rely on mucins to nourish the broader microbial network. When they are starved, the entire thermal regulation and cooling system loses its ability to function. This model shows a microscopic cross-section of the intestinal lumen under that unmitigated thermal overload. A severe oxidative stress cascade targets the epithelial wall. The tight junction proteins physically break apart, destroying the structural seals of the gut. Failing to maintain the logistical supply of that essential coolant physically degrades the intestinal firewall. This hyperpermeability ensures multi-organ distress and an ultimate mechanical breakdown of the barrier wall. Looking closely at this photograph of an unregulated food preparation environment, we see the direct introduction of high-risk external code. Ingesting street food during periods of acute environmental transition introduces severe biological friction. Injecting these unverified nutritional inputs bypasses standard local security protocols. It rapidly downloads corrupted data into the processor, causing immediate and massive systemic stress. This diagram tracks what happens next. Opportunistic rogue agents slip into the compromised lumen. They hijack the microbial registry and jam the thermal valve, converting bile acids into highly corrosive agents. This external code is a vector for malware. Sudden exposure enables the acquisition of antibiotic resistance genes, embedding directly into the microbial network. These genetic scripts upgrade the defense capabilities of rogue agents and neutralize future pharmacological countermeasures. This compounding effect of thermal overload, combined with unregulated dietary inputs, creates a permanent vulnerability in long-term system security. We see the inherited genetic framework here on the diagnostic dashboard. Specific sensor nodes, the TLR4 and FU2 genes, predetermine the operational capacity of the host's thermal regulation system based on regional ancestral programming. These genetic variations rigidly dictate local immune responses. They act as an automated filter, determining exactly which microbial communities are allowed to thrive in the gut by encoding specific antimicrobial peptides and mucins. To intervene effectively in this specific biological grid, engineers rely on precise metagenomic data. They deploy targeted biological patches that map perfectly to the host's genetic workforce to initiate system cooling. These specific multi-strain probiotic patches suppress the expansion of inflammation-driving rogue agents like Bilophila, simultaneously restoring the production of critical short-chain fatty acid coolants. Applying generic interventions during a thermal surge fails. True system stabilization requires absolute precision, aligning the biological patch with the regional genetic hardware to override transient dysbiosis. Even a fully patched biological system requires rigorous daily maintenance protocols to prevent a secondary meltdown during peak summer months. Operators must strategically filter raw material inputs. Prioritizing plant-based polyphenols provides the exact fuel beneficial units need to maximize production of molecular coolants. Looking again at our intestinal model, we see the results of successful intervention. But any probiotic patch utilized here must possess extremely robust stability parameters. It has to survive the brutal ambient temperatures of the Indian thermal grid long before it even reaches the digestive tract. To ensure this, operators must shield these biological inputs from environmental degradation. By blocking exposure to extreme heat, oxygen, and light, the integrity of the patch is preserved until deployment. Securing the regional grid through absolute environmental protection and targeted microbial maintenance is the only verified method to prevent mechanical breakdown within the intestinal engine.